We have been able to identify barriers and opportunities in all three scenarios for critical mineral production. There's more research to be done, but we're also closer to implementation. Now it's time to roll up our sleeves and get some of that done.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. Critical minerals play an essential role in modern technologies such as cell phones and computers, and those related to communications, national security, and energy generation and storage. Efforts are now being made across the United States to increase the nation's capacity for domestic supplies of critical minerals. We're joined today by Elizabeth Hawley, Associate Professor of Mining Engineering at Colorado School of Mines, whose group works to understand ore deposits and works with federal agencies and industry to improve mining operations. Dr. Hawley, thank you so much for joining us today.
Thank you so much for having me.
So the key thing we're talking about is a real exciting term right now, critical minerals. So for people that don't know what that is at all, what are critical minerals and why do we need them?
That is such a great question, and there are a lot of definitions for critical minerals. The Department of the Interior has a definition. The Department of Energy has a definition. There's a Trump executive order with a definition. And I think you can generally think of these as things that we need, but that may be vulnerable to supply disruptions. So the Department of Interior list has 50 minerals on it. The Department of Energy has what they call the Electric 18, that are 18 essential minerals and elements that we need for energy. And the new Energy Dominance Council can also add things to the critical minerals list. So probably think of it as about half the periodic table. We need these things for everything from agriculture to medicine to technology, energy, transportation. If it's part of our built environment, it has minerals in it.
Where are critical minerals, broadly speaking, mined in the United States?
The U.S. has about 60 operating metal mines on federal land that produced metals last year. Our work doesn't include things like aggregate, so gravel quarries, for example. We didn't look at coal. We didn't look at in situ processes like recovering uranium. But we have about 60 metal mines. And that also doesn't include those that are on state land or private land. So we're working with a data set of federally permitted metal mines. And we really only produce a few commodities from those mines. So we mine gold, platinum, palladium, zinc, rare earth elements, copper, and a few other things. And as you can guess, that does not add up to all of the minerals and metals that we need for our built environment. And so the rest of that is what we import.
So how much of what we do need are we able to produce here?
Are you asking what we're able to produce? Because I'm much more optimistic about that. Or are you asking what we do produce?
I think we're getting to what we could produce. Right now, like if there was a percentage, where are we at in terms of what we are able to domestically produce?
We are only producing a small percentage of the material that we actually mine. So if you think of a mine is a big rock moving operation, and a lot of rock is excavated and then it's processed, so its particle size is reduced, and then metallurgical techniques are applied to recover particular elements. And at most sites, you can think really any rock has quite a bit of the periodic table in it, and we're usually only recovering one or maybe up to something like 3 elements from that rock, and the rest is being treated as waste.
Thinking about the amount of critical minerals we have currently, I know we import a lot. Can you talk a little bit about our reliance on foreign supplies at this juncture?
I talked to you about how there are, about 60 U.S. federally permitted metal mines that operated last year. And the relatively short list of 10 elements that are produced and a few other byproducts that are recovered from those operations. And anything else on the periodic table would be something that we import. And in many cases, those are coming from foreign entities of concern, or they're coming from places that are politically unstable or where there are natural disasters and other issues that might disrupt supply. So the idea of criticality is really vulnerability. We can't get the things that we need unless we are importing them or unless we're producing them domestically. And our work identifies about 15 elements for which we are very highly import reliant at present. And if you take that list of 15 elements and you say, what if we recovered only 1% of what we actually mine and then throw away? We could eliminate imports. There's another group of about 10 elements where we would recover something like between 1 and 10% of what we mine and then eliminate imports. And then another batch for which up to maybe about 50% recovery would be necessary. And then there are a few elements of those most interesting, I think, are platinum and palladium, where there just isn't a lot in the rock that we have in the US. We have one operating platinum and palladium operation, which has 2 mine sites in Montana. And even if we recovered all the platinum and palladium that's in the other rocks that are being mined in the US right now, we still wouldn't be able to eliminate imports. So that shows you in a way that we really need that domestic operation in order to be able to continue supplying those minerals without being vulnerable to, for example, a lot of platinum and palladium are mined in Russia. And so there's a supply chain vulnerability there.
The work that you've produced that have brought us together today is talking about recovering more of this. Can you talk a little bit about what you're meaning by byproducts?
Our work that is funded by NSF looks at 3 different pathways for domestic critical mineral production. So we could produce critical minerals by opening new mines. For example, there's a cobalt mine that has been trying to open in Idaho. So this is a brand new operation that would target cobalt, where cobalt is not currently being produced, and that is a critical mineral. Another thing that we could do is look at our historic wastes. So if you think about all the mining that has happened in the past, some of it before environmental regulation, those environmental issues sort of dot the landscape, particularly in the West from metal mining, and we could go into those. We could also go into the accumulated wastes from today's active mines that have maybe been operating for something like 50 years. So they have quite a bit of waste accumulated, and you could reprocess that. Part of our work examines that. The third option is what we call byproduct critical mineral recovery. And so that is recovering today in that mine more elements than are currently being recovered. So if you imagine you're in your kitchen and you think about, well, I could, cut open a new orange. That's a new mine, right? Or I could dig around in my trash and see if there's a little bit of orange left over. Nobody would want to do that for food. That's gross. Sorry. And you could also say, well, I'm cutting up oranges and the way that I'm cutting them is kind of wasteful, and maybe I can get more orange out of what I'm already preparing and not put it in the trash. So that is what we're calling byproduct critical mineral recovery. It's getting more out of what we're mining today before it becomes waste.
Let's tease these processes apart a little bit. How might you be able to recover or make usable some of these versions? And I'm not sure which one to have you start with, but for the broader public, they might not have any difference between a copper mine and a gold mine and anything else, or even be aware that you can get so many different minerals from one piece of rock.
Our work takes a geological lens to this problem. So we're looking at all of the mines that are operating today, and we're categorizing them into particular geologic deposit styles. And then we're using that information to be able to draw out which elements are perhaps most abundant as potential byproducts. And that has to do with both the concentration in a particular geologic deposit style as well as the throughput. So, how much material is mined already from, say, a particular copper porphyry deposit. That's a type of copper deposit that we mine in the Southwest in the US. And so we're looking at what elements are associated with copper and could be recovered as part of that process, as opposed to only recovering the copper and putting the rest of those elements into waste. So, what our work allows us to do is be really thoughtful about where those other low hanging fruit exist so that the work can be done to make the recovery of those elements more efficient. And I think one of the really interesting outcomes of our work is that we found that there are quite a few elements for which you would only need to recover 1% or perhaps even less than 1% of what's currently being excavated and processed and not recovered. So you don't have to be perfect at recovering these elements. You could just recover a small fraction of them, and that would make a tremendous difference in terms of reducing our import reliance for a number of those elements.
Can you give us an example of any sort of technique that you would need to recover it from the past byproduct?
So if you're thinking past byproduct is what we're calling waste.
Sure. What was considered waste 50 years ago, let's say, at the copper mine, that you might be able to get some of these other elements out? What would you need to do with that waste to get to the other elements?
That's a great question. We recently published another paper in the journal Resources Policy on reprocessing mine waste for metal recovery. And if you think about it, it really depends on the condition in which that waste was left, whether it's behind something like a tailings dam or a tailings impoundment, as we call it, whether it's slurry material or simply piles of historic material on a hillside, for example. But that material would have to be collected up. Its particle size might have to be reduced. If it has weathered surfaces, for example, you might have to remove those. And then you would subject it to a metallurgical process, which could be hydrometallurgical or pyrometallurgical to recover additional elements. So I think that because of the heterogeneity of past waste, and it is an achievable thing, but it's going to take lots more research of the kind of work that our group does and other groups are doing across the country and across the world to be able to turn waste into value. It is a little bit easier in some ways to be working with an existing operation that already has material going through every day and to basically add another component to the processing circuit that might be able to recover additional material. So our work really helps identify where some of those low-hanging fruits might be. And if you had an element that you're particularly worried about for national security, for example, say it's gallium or germanium, our work points you to which sites might be most prospective for recovering those. And then the next step is to understand the mineralogical characteristics at that particular site, to understand how is this element, germanium, for example, in what mineral is it housed? How does that relate to other minerals? So that then you can understand what additional processing equipment you could include, what additional circuits you might need to be able to increase the recovery of that element.
Thinking about mining industry, is there challenge getting buy-in to the idea of approaching these, getting more recovery out of it, trying different things to change their business model? Like, are they open to change or suggestion of change?
Conceptually, yes, but there's a real disconnect between the market or the price environment for a critical mineral and how much we need it. And so in many cases, the byproduct recovery has been limited by, one, the fact that we might not have known it was there, and now our paper shows you how much is there. And two, perhaps some R&D needed to improve the processes to recover it. And three, the economic and policy context around byproduct recovery. So an operation is not going to be likely to recover something just sort of, out of good nature, right? It has to be economically justifiable, more capital in terms of building that processing equipment. There has to be a market for that. And that market has to be, would say, predictable enough to justify the investment. And one of the challenges with critical minerals is that, particularly for those for which the market is really controlled by China, there's an ability to flood the market and disrupt the price and make it very difficult for what I would see as responsible domestic operators to compete in that environment. So the next piece of this particular project that our group is looking at is what are the policies around byproduct recovery, and how do you incentivize that? It might not be worth it if you think about the simple dollars and cents, but are there other ways to motivate our domestic mining industry to do this and to make it worth their while?
It's like so much that we've done as a country historically is the tide kind of going in that direction to get everybody on board to do it. And I think that's something we're facing with critical minerals at this juncture.
Yes, I agree with you. And the announcement that came out from the Department of the Interior the other day with the USGS's new focus on waste as a source of critical minerals is really, really important. And as I mentioned at the beginning of our conversation, the past wastes are really the other side of the coin from the wastes that we're producing daily. And it's in some ways kind of similar to unlock both. Although I would say sort of the economic motivations are slightly different. There are some technical differences as well. But if we can really do both of those things well, we have completely changed the game in terms of access to the minerals and materials that we need as a society.
Part of this process was something called the Critical Minerals Mapping Initiative. Can you say what that is and how was its data useful for this work?
Yes, and it's actually a really neat story because it's kind of the origin story of our NSF project. I first heard about this database, which was being compiled by the Geologic Survey of Canada, Geoscience Australia, and the U.S. Geological Survey. And it got all kinds of ideas firing for me. So that is really part of the impetus for putting together our project, which we eventually then proposed to NSF. But a little bit more about that data set. We, in the past, have not analyzed ore samples for very many elements because as a society, we didn't use as many elements in our daily lives. And so if geologists were studying a particular region or a particular ore deposit, they were collecting data on a shorter list of elements. What this program did is basically pull in all of the historic samples that those three National Geologic Surveys had collected over many, many decades and reanalyze them for a list of 70 elements at very low detection limits. So as our project through NSF was growing, this database was also growing, which was really exciting for us. And when it hit 25,000 samples, we finally decided it was time to do this thing, which had been in the back of our minds for a really long time. And we built a separate database of U.S. mines and their annual production, what the main product was, the annual throughput. And then we paired that statistically with the tri-national CMMI database and used the kinds of ore deposits as sort of the filter. So you're looking at basically the same kind of rocks between this U.S. mine that you're trying to envision how many critical minerals are there, and you're looking at a large data set of similar samples from similar geologic environments. And then we used a statistical resampling technique to basically estimate with ratios towards the main product. Since, for example, germanium may never have been analyzed at this particular U.S. copper porphyry deposit where copper is mined. We don't know how much germanium is there. So we use this really big data set and a lot of really robust statistics to make ratios between the copper that is produced at the mine in the US and the germanium to copper ratios that occur in these same kinds of geological samples. And that gives us a really robust understanding of how much germanium could be in those rocks.
I also want to double back to the idea of collaboration there. Like in that initiative, there's multiple countries coming together. And I know you had a lot of people that worked on this particular project. Can you talk a little bit about how important collaboration is?
Yes. So that's what got us so excited about the Growing Convergence Research, or GCR, program within NSF. It read like it was written for us. We were trying to solve a compelling societal problem, and we felt that no discipline siloed on its own could crack this. And so the GCR program does exactly that. It uses deep interdisciplinarity to try to solve a really, really important societal problems. Critical minerals is one of those problems. And it allowed us to bring together 10 different disciplines. We are a group of scientists, engineers, and social scientists, and we work across all of those aspects as well as policy and interdisciplinary teaching to try to bring a really holistic framework to the critical minerals problem. And we've got 15 different projects. The one that I'm talking to you about today is just one of them. And they all are really interdisciplinary efforts that have benefited from not people going away and working in their own offices and labs, but in these kinds of deep conversations that really show all of the facets of the problem and help us identify where the gaps and where the opportunities are. So the work that we're talking about is one example that's come out of that, and we've done a lot of other really exciting things. And we feel that our project is an example of convening different disciplines and also different types of organizations. So we've got industry stakeholders, we've got government agencies, we've got community partners, and academics, of course, who are all working together on solving this problem. And that's the only way that we're going to be able to deal with this big beast that is critical mineral supply.
For my last question today, I want to think about the next few years in the future. What do you see happening as your projects are going ahead in the next decade, let's say? Or where would you like to go?
We have been able to identify barriers and opportunities in all three scenarios for critical mineral production. So that is new mines, byproduct recovery, and critical minerals from wastes. And I think we're at the stage now where there's more research to be done, but we're also closer to implementation. So we'd really like to scale up and move from the lab scale to potentially the pilot scale and ultimately commercial implementation, for example, of these new methods of production of critical minerals, because our goal really is both to understand the science and to move the needle in terms of what we consider responsible domestic production. So our work informs that, and now it's time to roll up our sleeves and get some of that done.
Special thanks to Elizabeth Hawley. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.